मैडम स्टार्ट करूंगा.
Okay, sir. Good afternoon, all of you. I, Archana Banai, working as an assistant professor in Computer Engineering Department, welcome you all for the session 6 under FDP Quantum Computing. It is great pleasure for me to introduce our distinguished guest for today's session, Dr. Vinod Pachghare, sir. I welcome you, sir, for the session. Dr. Vinod Pachghare, sir, is working as an associate professor in Department of Computer Engineering and IT Department with College of Engineering, Pune. Sir completed his graduation from Amravati University, post-graduation and doctorate from Pune University. Sir is having total 30 years of teaching experience. During this period, Sir published 30 plus research papers in reputed international journal as a main author, published and presented 30 plus papers in international conferences. He guided 25 plus projects of MTech. During his journey, he also worked for many research projects. A few of them are as follows. As a chief investigator for the Information Security Education and Awareness Project for Government of India from 2014 to 20, which cost up to 148 lakhs. Principal investigator for Wireless Intrusion Detection System for AICT from 2013 to 16. Investigator for the R&D project Innovation Detection System for the Institution of Engineering from 2009 to 10. Along with this, he worked as a consultant for many projects of cyber security. Sir published many books on the topics like cryptography and information security as well as cloud computing under the well-known publisher THR Learning, New Delhi. Sir coordinated 16 plus FDP and attended 30 plus FDPs till date. Sir is a member of well-known associations and societies like IEEE, CSI, ISTE, Computer Science Teacher Association, Science and Engineering Institute, and many more. Due to his valuable contribution to the academics, he is awarded with the Best Faculty Award by CSI in 2018. So we are lucky to have Sir for our today's session. Once again, on behalf of Computer Engineering Department, I welcome you, sir, for this session and request you to start your session. Thank you, sir.
Thank you, madam.
Over to you, sir. Over to you, sir.
Just a minute, madam. Sharing.
Yes, sir. Yes, sir. Yes.
Share option is not enabled here, basically.
Sir, present option.
Present now, okay?
Yes, yes.
Then your entire screen.
Yes, no problem, sir.
But what happened when I press it? It only cancel option is there. Share option is not enabled. That is the problem. I don't know why.
Actually, present now. Have you clicked on present now option?
Yeah. Okay. Then
your entire screen.
Press it.
Yes.
Then click on the window.
Your PPT, sir.
Click on the window.
Just a minute.
And then share. Click on share.
Yes, yes. Okay. Just wait.
Yes, yes, yes. It is coming. Yes, sir. Yes. Now your screen is shared here. Now switch to your window where your PPT is there.
It is visible now?
Yes, sir. Visible.
Yes, sir.
Okay. Okay. Thank you for the coordinator for inviting me for this session. and for all participants, be patient for next 1.5 hours. As this is the very emerging area, and you have lots of session basically on this quantum computing. So I am not taking the technical details of quantum computing, but what is the role of this quantum computing in various domains. So we'll start from this. This is the overview of my presentation. First, just the basic introduction of quantum computing, then some definitions, then what are the different features of quantum computing, then quantum computing versus classical computers, then applications of quantum computing, then what is the next step, or what is the role of computer science in quantum computing. Then because quantum computing is basically the branch of physics, so what is the role of computer science or computer engineering in quantum computing, that we are going to look. Then so every domain having some limitations also, so what are the limitations of quantum computing, that we are going to see. Then what is the post quantum era, and last we'll see the conclusions. Okay, so we start from the introduction. The field of quantum computing started in 1980s. It was then discovered that certain computational problems could be tackled more efficiently with quantum algorithms than with their classical counterparts. So this is the contribution of India. The Ministry of Electronics and Information Technology has, you all already aware about this MIT, has released a quantum computing simulation toolbox this last year, just in the month of September. This is also the first quantum computer simulator, that is QSIM toolkit in the country. That means India just entered in the field of quantum computing in the last year, basically in the month of March. First time ISRO launch or transfer the key securely. We'll see it, what is the distance and all those things later on. But the basically Ministry of, that is we can say MIT, having the grant and open the lab with Amazon, AWS, and they launched so many projects domain for this year. So those who are interested in research in quantum computing, they can visit the site of MIT. They can get the problem statement from there. So what is quantum computing? You have, I think, 5 sessions already on this domain. So, but just as a review, what is quantum computing? It is a study of how to use the phenomena in quantum physics to create new ways of computing. So it uses quantum mechanical properties to express and manipulate information as quantum bits or qubits. In our classical computing, we use 0 and 1. So here we can say we use the combination of 0 and 1 at the same time, so that is qubits. So it is an area of computing focused on developing computer technology based on the principles of quantum theory. Okay, what is quantum theory? It explains the behavior of energy and material on the atomic and subatomic levels. Basically, it is the branch of physics. So we take the advantage of those things for using computer science or engineering. So what is quantum? It is the smallest possible discrete unit of any physical property. It is usually referred to properties of atomic or subatomic particles such as electrons, neutrons, and photons. Now qubit. Qubit is the basic unit of information in quantum computing. It plays a similar role in quantum computing as bits plays in classical computing. We already aware that we are computer engineers. I hope most of are engineers, so we know what is 0 and 1. So those are the basic units. So qubits plays a similar role in quantum computing as bits play in classical computing, but the behavior is different. Classical bits are binary and can hold only position of 0 or 1. They may be in computer either 0 or 1, only true or false states are there, but in qubits can hold a superposition of all possible states. What is superposition? It is one of the features we'll see later on. Computers used today can only encode information in bits that take the value of 1 or 0, so restricting their ability. On the other hand, quantum computing uses quantum bits or qubits. It harnesses the unique ability of subatomic particles that allows them to exist in more than one state. So that is a 1 or a 0 at the same time. Quantum computing is made up of qubits. So qubits is the basic unit in quantum computing, like 0 and 1 in classical computing. What quantum computing can do? It can be used, some of the belief that where we can use it is basically the most important role of quantum computing is factor primes. You know, encryption algorithms. That means in cryptography, so many encryption algorithms are there. One of that is RSA. And if you are aware that RSA is based on the fact that factoring large primes. That means we have to select the prime number and the factors of that number. So using the key size, because for RSA the key size is variable, and for most secure key size today is 2048, because 1024 is not secure. So the suggested secure key is 2048 bit. It could take millions of years on a supercomputer which are existing today. It takes millions of years to find out the factors of the prime number having the size 2048 bit. But quantum computers could do this in minutes. That is the difference between the classical computing and the quantum computing. So but this is theoretically, see here, quantum computers still not exist that much power, but it is assumed that quantum computers can do this in minutes, while the classical computing it takes millions of years. Then second is secure communication. Quantum-based networking allows perfectly secure communications. That means what is the problem of today's cryptographic algorithms or encryption algorithms? If you say the symmetric or asymmetric, both there is some parameters you have to transfer to the receiver. Now what happens? Eavesdropper, that means the third party, he can listen the communication between the two authorized entities, and in that case that is called eavesdropping. So quantum based networking allows perfectly secure communications. Any eavesdropping on the signal destroys the signal. That means when the key is transmitted using quantum computing from one place to the another place, if the third party tried to capture the key, the signals are destroyed, and hence the signals are destroyed, the key is no more useful at the receiving end. So receiver knows that this is not the proper key. So any eavesdropping on the signal destroys the signal. Hence quantum networks are perfectly secure and invulnerable to hijacking. It is used to solve a variety of problems that are hard for digital computers. Some of the example is random walk problems and classes of NP problems may be tractable with quantum computers. Solve quantum mechanics, material science problems. What better to solve quantum mechanics problem than a quantum computer? That is the best solution to solve the quantum mechanics or material science problems. But they are not a panacea. They will not replace. That means it is not the complete replacement for digital computers, because for day-to-day tasks. That means if suppose we want to make 2 plus 3, orally you can do it, 2 plus 3 is 5. Can we use the calculator? Whether a calculator is more faster for such type of addition? No. It depends upon what type of addition or what type of calculation you want to perform. Accordingly, the usage. In the same way, for 2 plus 3, we can make it 5 immediately. So if we want to use the calculator, it takes more time. In the same way, if we compare the digital computer and the quantum computer takes more time as compared to digital computer, day-to-day tasks. For example, suppose for execution of small program and all those things. But that means they will not replace digital computers for day-to-day tasks. We still need digital computer for this activity. Enormous quantum power is there. For example, a 60-bit computer can perform manipulation on 64-bit binary numbers at a time, while 64 qubit quantum computer operates in a space of 2 raised to 64 dimensions. That means 16 into 10 raised to 18 numbers to specify the state of the quantum system. That is the power of the quantum computing. It also means you double the power with every added qubit. For example, to double the power of a digital computer, now you know that 32-bit or 64-bit. Okay. In classical computing, where to double the power of a quantum computer, you just have to go for one more qubit. That is 32-bit qubits should be replaced by 33 qubits. That is the power. Now, Shor's algorithm. Some of you may aware that what is the Shor's algorithm. Basically, it is the algorithm for quantum computer algorithm used to factor the prime number. Okay, prime factors, basically find the prime factors of a number. Yeah, so prime factors means the number n may not be prime, but that's why it's having some factors. What are the factors of those should be the prime. For example, you can say, you can take any one example like 10. What are the factors of 10? 2 and 5. 2 is prime, 5 is also prime. So these are the prime factors of number n. N is 10. So n algorithm that runs on a quantum computer that finds the prime factors of a number n and does it in polynomial time rather than exponential time as on digital computers. That means suppose some number n is 5 digits, 6 digits, 7 digits, because it is suggested that in cryptography n should be large. So if n should be large, the prime factor is also large, and the number is large, it takes more time. So in digital computer, it takes exponential time, but using quantum computing, it takes polynomial time. So that is time required is less as compared to the digital computer. What would take a normal supercomputer tens of millions of years can be done in minutes on a quantum computer. Okay, that means that is the power of quantum computer. Since most encryption algorithms, some example like PGP and RSA, rely on a public key n, which is composed of 2 large primes. Quantum computer could crack that encryption in minutes rather than millions of years on a digital computer. Now, how we can make the use of quantum for communication? That is quantum communication. Unhackable communication is possible. Using the properties of quantum entanglement, quantum communication is immune to man-in-the-middle eavesdropping. What is man-in-the-middle eavesdropping? Those who are familiar with cryptography and Diffie-Hellman algorithm, basically Diffie-Hellman algorithm is suffered by man-in-the-middle attack. What is man-in-the-middle attack? Suppose, for example, if you want to send some message physically to your friend, how you can transmit the message? You can just simple example, you can write something on the letter, insert that letter on some paper, insert that paper in some envelope, seal it, sign on the side and send it. Now what happened? As the envelope is sealed, it is not possible for the postman or the courier boy to read the message. But if at the same time, if you use the postcard, write something on that and send it, now anyone in between can read the message. That is the person in between, courier boy or the postman is man in the middle. In the same way, I will not want to discuss more in DP-Hellman or anything else. What happened? Some algorithm, basically DP-Hellman algorithm is suffered by man in the middle attack. That means third party can capture the keys or some initial information, generate the key and communicate with sender as well as receiver in the both the ways. So using the properties of quantum entanglement, quantum communication is immune to man in the middle eavesdropping. Okay, man in the middle is not possible in quantum computing. So that is unhackable communication is possible. Anyone trying to listen to the communication breaks the entanglement, rendering the eavesdropping useless. That means anyone trying to listen to the communication breaks the entanglement. Entanglement is one of the property. If that property or that feature is broken, rendering the eavesdropping useless. That means eavesdropping is not possible in this case because it is identified. Now we'll see the features of quantum computing. Superposition and entanglement are two features of quantum physics on which these supercomputers are based. We'll see these properties. This empowers quantum computers to handle the operations at speeds exponentially higher than conventional computers and much lesser energy consumption. That means energy consumption is less and speed is also high. Today everybody expects high speed. So that is provided by the quantum computing. What is superposition? In superposition, quantum particles are a combination of all possible states. They fluctuate until they are observed and measured. One way to picture the difference between binary position and superposition is to imagine a coin. So what is the difference? What we can say? Suppose classical bits are measured by flipping the coin and getting heads or tails. That means when we flip the coin, what are the two positions? Either we get head or tail. So this type of calculation or imagination is happening in classical bits, 0 or 1. But in case of quantum computing, if you are able to look at a coin and see both the heads and tails at the same time, because the coin is in the air, and you can at the same time you can see different positions, heads and tails, and at the same time. So as well as every state in between, because the coin is rotating, so you can see different states. Every state in between, the coin would be in superposition. Instead of only head and tail, you can get different positions of that coin. So that is called in superposition. So the first figure in the left hand side, it indicates classic bit, that is either 0 or 1, head or tail. But when you can see in the angle of quantum computing, you can get different, when the coin is taking different rotations while coming towards the ground, you can see different positions of that coin instead of head and tail only. So it is qubit. Now next feature is entanglement. Entanglement is the ability of quantum particles to correlate their measurement results with each other. That means when they are coming, we can correlate the results. That is called entanglement. Different positions we can capture, we compare with each other, and that is the entanglement. When qubits are entangled, they form a single system and influence each other. Okay? That means at the same time you can see head and tail, both head, both tail, like this way. That is 0, 0, 0, 1, 1, 0, 1, 1. So it makes the combination of like this way. We can use the measurements from one qubit to draw conclusions about the other. By adding and entangling more qubits in a system, quantum computers can calculate exponentially more information, and it is used to solve more complicated problems. These are some of the domains where quantum computing contribute? Some of the domains: finance, military affairs, intelligence, drug design and discovery, aerospace designing, nuclear fusion, artificial intelligence, digital manufacturing. What is the basic difference between quantum computers versus classical computers? Before going to the some domains where exactly quantum computing can contribute, we will see what is the difference and what is the current state of the quantum computing. So quantum computer versus classical computer, we see quantum computer process information differently, while classical computer use transistors which are either 1 or 0. Quantum computers use qubits which can be 1 or 0 at the same time. That is the first difference. Say the number of qubits linked together increases the quantum computing power exponentially. But meanwhile, linking together more transistors only increase power linearly. In case of classical, the power is increased linearly. Classical computers are best for everyday tasks, day-to-day tasks. There is a need of classical computer till date. But quantum computers are great for running simulations or data analysis, such as for chemical and drug trials. You can see, if so, there are so many databases already, you may be aware, data sets are available. Huge data is generated every day, and to process this data, classical computers may not support for this thing. So quantum computer is in picture, which are great for running simulations and data analysis, such as for chemical and drug trials. This computer must be kept ultra cold, however. That is the things. That means there is a need. If you see in the 90s or 1995, that time AC is compulsory in computer labs. All sir may be aware these things in at Sangamner also. This computer must be kept ultra cold. Quantum computing currently. But what happens if you consider classical computers? Whether AC is required today? No. So in the same way, current position of quantum computing is this computer must be kept ultra cold due to huge heat generation, and they are also much more expensive and difficult to build. Classical computing advances include adding memory to speed up the computers. Just add the memory, you can get the more speed. Quantum computers help to solve more complicated problems. While quantum computer might not run Microsoft Word better or faster. That means for small applications, quantum computers are not useful. They can run complex problems faster. For example, Google's quantum computer that's in development. See here, it is not developed state. It is in the development. Could help with many processes such as speed up machine learning training or help create more energy efficient batteries. This is the just example. Google in 2019 proved that a quantum computer can solve a problem in minutes, while it would take a classical computer 10,000 years. Now, these are the different companies which work in the field of quantum computing. IBM, Microsoft, Google, DWave System, Alibaba, Intel, and many more are there. Percentage of large companies planning to create initiatives around quantum computing by 2025 as per Gartner report is 40%. And today only 2 countries are heading in, basically one is US, second is China, after that European Union, and then India enter in the era of quantum computing. So a real world example of a quantum computer is Google spending billions of dollars on its plans to build its quantum computer by 2029. The company has opened a campus in California called Google AI to help it meet its goal, and has been investing this technology for years. So for 2029, they are planning. Honeywell International and IBM is also the players in the quantum computing. IBM expect to hit major quantum computing milestone in the coming years. That is, IBM plan to have 1,000 qubit quantum computer in place by 2023. So next 2 years you can say, we may have a quantum computer. For now, IBM allows access to its machine if they are part of its quantum network. See, Google is not allowed, but IBM allows access to its machines.
Sorry to interrupt in between. Deepak Patil sir, please mute yourself. Deepak Patil sir. Thank you, sir. Sir, you can continue now.
Okay, thank you, sir. For IBM allows access to its machines if they are part of its quantum network. So those who want to work on quantum computing, this is the news for them. Those that are part of the network include research organizations, universities, and laboratories. Microsoft also offers companies access to quantum technology via the Azure Quantum Platform. This is unlike Google, which doesn't sell access to its quantum computers. So for the researchers, Google is not there, but they can go for IBM or Microsoft. Definitely, they can work on the some for the research domain. Okay. Then, what are the applications of quantum computing? Quantum computers are ideally suited to solving complex problems which are hard for classical computers, but they are easy to factor on a quantum computer. Such an advancement creates a world of opportunities across almost every aspect of modern life. Now, Google has recently made headlines proclaiming the achievement of quantum supremacy, where its computer can perform a task that a conventional computer can't. That is the announcement by the Google. Just a minute. सर लेक्चर मध्ये okay. IBM is also making noise about their supercomputers because there is a competition for different companies who is the leader in this domain. So IBM is also making noise about their supercomputers, which are blazingly fast. However, we often wonder what these things actually do and what are its real world applications. Because everything is on paper, they are trying to implement what is the outcome we may see after some time. Now we'll go for the role of computer science in quantum computing, or what is the role of quantum computing in computer science. Either way, they should be in hand in hand. So quantum cryptography, it is cryptography of 21st century. So first, the role of quantum computing in computer science. That means cryptography, that is the branch of now computer science. Now how we can use quantum cryptography? So basically classical cryptography, some of the algorithms are coming in DS long back, but now it is nowhere. Now currently AES is there. नंतर बोलू का तुम्हाला मी लेक्चर मध्ये आहे थोडा हो सर मी फोन करतो तुम्हाला नंतर so Quantum cryptography is cryptography of 21st century. Why this statement is there? Because the current, whatever the traditional cryptography is there, now currently most of you are aware that AES is most popular algorithm for cryptography today. Everybody pronounce that cryptography means AES algorithm. But what happened? Nobody knows that after 2 years or 1 year, it is not the secure algorithm, maybe. So there is a need of more secure algorithm. So quantum cryptography is cryptography of 21st century. An important feature of quantum cryptography is that security of quantum cryptographic protocols is based on the laws of nature, that is on quantum physics, and not on the unproven assumptions of computational complexity. Okay, that means quantum cryptography, what is the feature? Security of these algorithms. Whatever the algorithms are going to in the quantum cryptography, they are based on the laws of nature, that is on the quantum physics, and not on the computational complexity. What is computational complexity? Today's algorithm, you can take the example of RSA algorithm. What is the computational complexity? Large numbers and the prime factor should be large. Okay, you have to select largest prime number. This is the sentence of the RSA or differential algorithms. That means the complexity of those algorithms, security of those algorithms is based on the prime numbers, largest prime number. But what happened? In quantum cryptography, quantum computing is used, we already see that within a minute or some seconds, the factors are possible of any number, any large number. So now quantum cryptography protocol is based on the laws of the quantum physics now, in which whatever the size of the key, you can transmit the keys securely. That is the basic concept. Now how we can transmit the keys securely? That is the basic theme of the quantum cryptography instead of computational complexity. Quantum cryptography was first proposed by Stephen Wisner in the early 1970s. In the very first slide introduction, I mentioned that the quantum computing was initiated or start in 1980s. But here it is mentioned that was first proposed by Stephen Wisner in the early 1970s. The concept just, but the proposal was published in 1983. That's why the quantum cryptography is initiated after 1983 only. So the proposal was published in 1983 in SIGAT News, and by that time, two scientists, Bennett and Brassard, who were familiar with Wisner's ideas, were ready to publish their own ideas. Here, Stephen Wisner having this idea of quantum cryptography in 1970s, and these scientists Bennett and Brassard familiar with these ideas, so they published their own ideas using the same base in the same time. Now what happened? In 1984, they produced the first quantum cryptography protocol, the BB84. So BB means their names, Bennett and Brassard, and 84 that year. So the first quantum cryptography protocol was published in 1984 and the name was BB84. This is the idea on paper only, theoretical things. The first, because most of the quantum computing theory is on the paper only, implementation is far away. The first experimental prototype based on this was made in 1991. That is implementation of this BB84 in 1991. It operated over a distance of 32 centimeters here. Only 32 centimeters. Over time, the technology has been refined and the distance increased to kilometers. Because 32 centimeters is not that far, but it was the experiment, and now currently it increased to kilometers. So quantum cryptography is the first area of information processing and communication in which quantum particle physics laws are directly exploited to bring an essential advantage in information processing. It has been shown that would we have quantum computer, we could design absolutely secure quantum generation of shared and secret random classical keys. That means basically everything is security of the algorithm is based on the security of the keys, how you can transmit the key. So quantum computer can be used for the transmission of the keys. How you can share the keys? It has been proven that even without quantum computers, unconditionally secure quantum generation of classical secret and share keys is possible, in the sense that any airdropping is detectable. That means without quantum computers, if you transmit the keys securely, it is possible, but in actual life, airdropping is there. So if airdropping is detectable, then we can say it is possible to transmit the secure. That means secure transmission of the keys is possible. Unconditionally, secure basic quantum cryptography primitives such as bit commitment and obvious transfer are impossible. Quantum teleportation and pseudo telepathy are possible. Then quantum cryptography and quantum networks are already in advanced experimental stage. Quantum cryptography is an attempt to allow two users to communicate using more secure methods than those guaranteed by traditional cryptography. In traditional cryptography, security relied on the mathematics and took into account the limited computation powers that we have developed. That means everything is, you may be aware about the number theory. So most of the cryptographic algorithm depends upon the mod and prime numbers and log and all those things. So traditionally, cryptography security relied on the mathematics and took into account the limited computational power that we have developed. And we assume that using those power, it is not possible to find out the prime factor and all those things. Breaking a cryptographic code would involve factoring extremely large numbers into two primes, typically of over 100 digits in length, which was assumed to be impossible in a reasonable amount of time, less than a million years. A reasonable amount of time. Even if all of the available computers today work exclusively on one such problems. That means that is the today's scenario about the classical cryptography. But however, just because there is no algorithm efficient enough to do the factoring quickly does not mean that such an algorithm could not be found eventually. That means in due course of time, if some algorithm is there and which is we can be able to find out the factors of any large number, then this classical cryptography will collapse. So quantum cryptography, which uses photons and relies on the laws of quantum physics instead of extremely large numbers. Now see here, large number is no value in quantum cryptography. So this is the cutting edge discovery which seems to guarantee privacy even when assuming airdroppers with unlimited computing powers. That means airdropper means the attackers who can listen your communication without your knowledge. So we can see the quantum cryptography is not depend upon the large prime number and all those things. The process of quantum coding. Quantum cryptography is not replacing traditional cryptography. It is not the replacement for the you can say classical cryptography. Rather, it allows for a more secure transfer of the keys used in encoding and decoding. Okay, so the security of our home, it is not depend upon the which lock you are using. Yes, definitely some contribution of the lock quality and all those things is there, but the thing is that if you are using the 5,000 rupees cost of the lock, Godrej lock, suppose you can assume, and the keys is at the top of the door, whether you can say it is secure, your home is secure. If the attacker knows that the key is at the top of the door, whatever the lock is there, what is the cost and what is the quality of the lock, he can take that key and open your door. In the same way in the cryptographic algorithm, whatever the cryptographic algorithm you are using, if your key is not secure, then so quantum cryptography basically, the application of quantum cryptography basically to allow for a more secure transfer of the keys used in encoding and decoding. That means how we can distribute the key. That is the we can use quantum cryptography for distribution of the key. The amount of information which can be transferred using quantum cryptography is not very large or very fast, but it is very secure. That means we don't have to concentrate on the size or the speed, we have to consider how it will be secure. And how it is possible, we will see. The maximum speed, scale, and security of the transfer is achieved by sending the secret key using quantum coding. But encoding and sending the data itself using traditional methods and algorithms. Okay, that means you can use our traditional algorithms, traditional methods, but use the quantum computing to transfer the key securely. This way the users can ensure more privacy by making sure their key is as secure as modern technology can make it, while still transferring the information as quickly as possible. Information exchange refers just to the secret key. See here, just one example how we can provide the security and all those things. You have ATM card and all those things. Previously, now that means you can withdraw when you can enter the PIN in the ATM. You can withdraw your cash. Now what happens if the cash is more than 10,000? The OTP is there. That is one more layer of security they provided you. Less than 10,000 you can withdraw easily using PIN. But if the amount is more than 10,000, more layer of security is provided. That means they send the OTP on your phone number, and now somebody having your PIN as well as ATM card, he can't withdraw more than 10,000. So some type of security provided. Here also it is there. Only the key, we have to provide the security to the key. Algorithm remains same because AES algorithm is openly available. So each and every step is mathematical calculation, everything is available. What is the new thing we have to add? We have to add only the key, which is the security of that algorithm. So information exchange refer just to the secret key, which is later used to decode the bulk of the information, not to the information. That means quantum cryptography is used to transmit the key securely and not your data. So outline of the process. In quantum cryptography, data is converted to bits of zeros and ones and then transferred using polarized photons. Photons are put into a particular quantum state by the sender and are observed by the recipient. Okay, that means first data is converted, because when we have to give any type of data before transmission, computer should convert it in terms of 0 and 1. Okay, then transfer this using polarized photons. That is the quantum computing concept we have to use for this thing. Then these photons are put into a particular quantum state by the sender and are observed by the recipient. A photon can be one of 4 polarizations. These are the states: 90 degree, 0 degree, 45 degree, and minus 45 degrees, and can be measured using 3 different bases: rectilinear, that means horizontal or vertical; circular, left circular or right circular; and diagonal. Okay, so what happens? Only the rectilinear and circular bases are used here in quantum cryptography. The receiver can distinguish between 0 and 90 degrees or minus 45 and 45 degree polarizations. Due to the physical principles, a measurement destroys the photon, because when you measure something, it destroys the photon. So it is impossible to carry out both observations. So either you have to do 0, 90 or minus 45 and 45 degree observations. Now thus the receiver not only needs to receive the signals but also measure them with respect to the correct basis. That means when the sender convert this into quota and send it, at the receiving end, the receiver with the signal receives the signal, and at the same time he should measure with respect to the correct basis. Now this information cannot be transferred between the sender and the receiver if intercepted, would allow third party to obtain the secret key. That means suppose this information is sent by the sender, instead of the recipient, some third party or the attacker try to capture or try to gain the information, the signals are destroyed and the receiver doesn't receive the information at that time, and he knows that he not received the information. That means the key is hacked by some attacker. Instead, the receiver randomly chooses one of the two it either distinguishes between a 0 and 90 or minus 45 and 45 degree polarization for each signal. Then the receiver contacts the sender by any means of communication and publicly discusses which type of measurement was done for each bit. Then he asks. So without contacting to the sender, the attacker can't, if the attacker capture the signals, but he don't have the information which is the measurement type. So if the attacker is not there, the signal is at the receiving end, he contacts the sender and publicly discusses, that means openly discusses, no harm for this, which type of measurement was done for each bit. The sender confirms which types were correct, and the sender and the receiver both discuss the bits that weren't measured accurately, and this constitutes the key. And now in this way the key is formed. So this is experimental cryptography. And today, what are the success they received from this? Transmission using optical fiber to the distance of 120 kilometer. Now currently it is up to 120 kilometer. Now open air transmission to the distance of 144 kilometer at daytime. That means this is the experimental results they achieved. As far as India is concerned, where is India in quantum computing? ISRO, everybody knows, has tested a free space quantum communication over a distance of 300 meters in the last month, that means March 2021. Okay, that is the first time they achieved the success and enter in the quantum computing race. Only see here, what is the difference? 120 kilometer, 144 kilometer, and we have only 300 meters. All current systems use optical means of quantum state transmissions. What are the problems then? No single photon sources are available. That is one of the problem, or you can say issues. Loss of signals in the fiber. So current error rate is 0.5 to 4%. So if signals are lost, then automatically whatever the signals received at the receiving end may have different effect of it. To move from the experimental to the development stage, that means we have to deploy the whatever the algorithms, or you can say any system. When you get some model, you have to deploy it. Before that, now currently we are in the experimental stage. We means the work in the experimental stage. So when it will become in the developmental stage, some time, then what are the basic difference between classical versus quantum cryptography? Security of classical cryptography based on unproven assumptions of computational complexity. Security of quantum cryptography based on laws of quantum physics that allow to build systems where undetectable airdropping is impossible. That means undetectable airdropping attack is impossible. In the other way, airdropping is detected in case of quantum cryptography, where it is not possible. That means suppose the postman or the courier boy read the message from your postcard, whether you can detect it? No, it is not possible. We don't have any way, because you not alter the message. If you are from the security domain, you may have the passive attack and active attack. So passive attack is difficult to detect. So in the same way here, but what happened in security of quantum cryptography? Someone tried to capture the signal in between. The signals is not, that means completely there. Quantums are positions are changed and are modified, and at the receiving end it is immediately detectable. So detectable airdropping is possible in case of quantum computing or quantum cryptography. Since classical cryptography is vulnerable to technological improvements, it has to be designed in such a way that a secret is secure with respect to future technology during the whole period in which the secrecy is required. Quantum key generation, on the other hand, needs to be designed only to be secure against technology available at the moment of key generation only, not other part. The next domain where quantum cryptography can be used. in artificial intelligence. Everybody knows that today data science, artificial intelligence, machine learning, these words are, everybody wants to work in these domains. Okay, so what is the role of quantum computing in artificial intelligence? The prominent areas right now. However, as the number of applications increased, it becomes a challenging task for traditional computers to match up the accuracy and speed. As the number of applications increased, it becomes a challenging task for traditional computers to match up the accuracy and speed. You know that what is the accuracy, what is the speed is required nowadays. And so applications are increased, data set size is also increased, number of data generated, huge data generated every day. So it is a challenging task. So, and that's where quantum computing can help in processing through complex problems in very less time, which would have taken traditional computer thousands of years. So it is directly the replacement in that case. That means traditional computers can be replaced by the quantum computers because huge data is processed within a very less time. That is the advantage of quantum computing. Then quantum machine learning. It is a research area that explores the interplay of ideas from quantum computing and machine learning. I think everybody is familiar with machine learning. So it is a symbiotic association, leveraging the power. That means it is not advantage to the machine learning area, but machine learning also useful for quantum computing, both the ways. So it is a symbiotic association, leveraging the power of quantum computing to produce quantum versions of machine learning algorithms, and applying classical machine learning algorithms to analyze quantum systems. For example, we might want to find out whether quantum computers can speed up the time it takes to train or evaluate a machine learning model. You know that machine learning model have training and testing. Huge data is available for training, so it takes lots of time to train the model. And then only we can have test the data. Okay, so if we might want to find out whether quantum computers can speed up the time, so very less time is required. For example, you can take the example of again from security, intrusion detection system. Huge number of packets are coming, and the system have to in the real time identify whether the intrusion or not. So for this, each and every packet should be processed. So if the model is required to train and test these things, high speed is required. So for real time experimentation, so quantum computer may be useful for this thing. On the other hand, we can leverage techniques from machine learning. That means quantum computers can be speed up the time for machine learning. On the other hand, we can leverage techniques from machine learning to help us uncover quantum error correcting codes. If suppose there are some errors, we have to run some uncover quantum error correcting code. That means those errors which are not covered. So we can use machine learning techniques to cover the error correcting codes, estimate the properties of quantum systems, and develop new quantum algorithms. The limits of what machines can learn have always been defined by the computer hardware we run our algorithms on. It is basically based on computer hardware. Because if the data set is large, any algorithm working on, suppose you want to compute the entropy of the 10 lakhs records, it's difficult for your machine to get the output immediately, or information gain. So the limits of what machines can learn have always been defined by the computer hardware we run on our algorithms on. So that is GPU and all those things are there nowadays. We can take the help of them, or cloud. For example, the success of modern day deep learning with neural networks is enabled by parallel GPU clusters. Quantum machine learning extends the pool of hardware for machine learning by an entirely new type of computing device, the quantum computers. That means quantum computer high speed, so it can be directly replacement for the GPU cluster. Now quantum computers like neural networks. So quantum computers can be used and trained like neural networks. We can systematically adapt the physical control parameters such as an electromagnetic field strength or a laser pulse frequency to solve a problem. For example, a train circuit can be used to classify the content of images by encoding the image into physical state of the device and taking measurements. Then what is quantum data? It is any data source that occurs in a natural or artificial quantum system. This can be data generated by a quantum computer. Quantum data exhibits superposition and entanglement. These are the features. Okay, so quantum data exhibits superposition and entanglement, leading to joint probability distributions that could require an exponential amount of classical computational resources to represent or store. That means whatever the quantum data, for classical computational resources, it is not possible to process those things. It takes lots of time. The quantum supremacy experiment showed it is possible to sample from an extremely complex joint probability distribution of 2 raised to 53 Hilbert space. The quantum data generated by NISQ processors are noisy and typically entangled just before the measurement occurs. So heuristic machine learning techniques can create models that maximize extraction of useful classical information from noisy entangled data. So now the next, finance. So each and everybody is related to after 2017. So now e-commerce, everything is online. So quantum computing has to play the major role in finance. So the quantum world may seem to be light years away from business as usual. Okay, so we can predict today. Okay, quantum computer is there. This is the quantum computer like this way. How many institutes have now supercomputers themselves? Some IIT, CDAX, and all those things. Others, nowhere there. So whether quantum computing is also in the same way. So quantum world may seem to be light years away from business as usual, but it has become clear that quantum computing, even in its infancy, holds great potential for finance and accounting. So it's a potential finance and accounting world must start preparing now for quantum computing. The technology will affect applications where optimization plays a role, such as stock forecasting and supply chain management. Risk analysis and fraud detection are also areas in which quantum computing is likely to have an effect. That means we can use the quantum computing applications in risk analysis as well as fraud detection also. In finance and accounting application, some domain where we can use the quantum computing is forecasting, transaction processing, and trading. So it is interesting in finance and accounting applications where optimization plays a role. Another area is risk analysis and fraud detection. So we could do real-time fraud detection and analysis through these applications. That is also possible. Okay, these are the assumptions. Currently, nothing is happened there. So these are the assumptions that once the quantum computing is there, so we could do real-time fraud detection and analysis through these applications. Now, quantum computing as a threat, yes. When there are some good things, bad things also coming. So that is the byproduct. So financial institutions deal with very sensitive customer data as well as information regarding transactions and contracts. Moreover, regulators require this data to be stored for periods ranging from several years to several decades. Therefore, it is paramount that it should remain secure and private. Because we have to store the data. How we can store the data? It should remain secure as well as private. So privacy is concerned. Some of the encryption algorithms used today rely on complex mathematical problems that classical computers can't solve. If all classical computers would work together to break an encryption key, this would take approximately 14 billion years. That is the security. But what happened? However, it has been theoretically proven that a quantum computer would be able to break some types of encryption in a matter of minutes or seconds. हॅलो सर, मी लेक्चरमध्ये फोन करतो तुम्हाला. It has been theoretically proven that a quantum computer would be able to break some type of encryption in a matter of minutes or seconds. That means for cryptography, quantum computer is very good. You can say gift. But what happens at the same time, using quantum computer applications, you can break the key. And several algorithms that can do that have already been developed. Whatever the algorithm, yes, you can say secure. RSA 2048. We know that RSA, we can select any size of the key, that the key size is variable. So we can say that means 4000 something. But it may be secure. But what happens if quantum computing is in picture? It is possible to break this key also. So that is the threat. So quantum hardware hasn't yet reached the necessary level of development to run such algorithms. That is the fact. Key hardware is the problem. It is not at that level necessary development to run such algorithms. So these algorithms is on paper only. Nevertheless, as soon as large-scale fault-tolerant universal quantum computers become available, there is a risk that all the data and private information concerning people, businesses, and transactions may be exposed. Now, how quantum computing has an opportunity? Optical arbitrage, credit scoring, derivative pricing, all these financial processes involve many mathematical calculations and become even more complicated and resource intensive as the number of variables increases. At some point, people have to settle for less than optimal solutions because the complexity of the problem surpasses the capabilities of the current technology and methods. These so-called intractable problems that can't be solved by a traditional computer in a reasonable amount of time. This represents the best use cases for quantum technology. That means you can give this as input to the quantum technology. You can consider this as the raw material and develop the algorithms for this. One of the most acclaimed applications of quantum computing is the financial sector, where the accurate simulation of markets and the ability to predict how a change in a commodity price will influence the cost of other assets. Quantum computer would be to perform so-called Monte Carlo, may be aware about Monte Carlo method. So Monte Carlo simulation to forecast future markets, predict the price of options, and assess risk and uncertainty in financial models. By optimizing machine learning and employing algorithms capable of recognizing patterns in large amounts of data, quantum computers could perform these highly complex forecasts and predictions. Now we use only machine learning on our classical computers or traditional computers, but it takes lots of time if the huge data is there. But using quantum computing, it is possible in less than a minute. Then trading and portfolio optimization are other areas where quantum computing could significantly help. So traders are currently limited by computational limitations and transaction cost in simulating a large number of scenarios and improving portfolio diversification. Scientists have already proved that quantum technology can deal with the complexity of these problems. Then these are some of the fields where again we can say quantum computing can be. So I want to skip these things. That is computational chemistry. Here it also can be used. Then drugs design and development. Then logistic optimization. These are some of the areas. Weather forecasting we can see because of huge data generated and there is a very need because in US or in UK, you can say European countries, they can give the correct prediction about the weather. But in India, this is still we are lagging for these things. A quantum computer ability to crunch vast amounts of data in a short period could indeed lead to enhancing weather system modeling. This allowing scientists to predict the changing weather patterns in no time and with excellent accuracy, something which can be essential for the current time when the world is going under a climate change. Weather forecast includes several variables to consider, such as air pressure, temperature, air density, which makes it difficult for it to be predicted accurately. Application of quantum machine learning can help in improving pattern recognition, which in turn will make it easier for scientists to predict extreme weather events and potentially save thousands of lives in a year. Okay? That means where the benefit of quantum computing in weather forecasting. With quantum computer, meteorologists will also be able to generate and analyze more detailed climate models, which will provide greater insight into climate change and ways to mitigate it. Then it is also used for navigation because GPS system can't work everywhere on the planet, particularly underwater. That is the limitations of the GPS system. So quantum computing requires atoms to be supercooled and suspended in a state that renders them particularly sensitive. In an effort to capitalize on this, competing teams of scientists are racing to develop a kind of quantum accelerometer that would yield very precise movement of data. One promising effort is happening in France. An effort to build a hybrid component that pairs a quantum accelerometer with a classical one, then uses a high-pass filter to subtract the classical data from the quantum data. The result, if realized, would be an extremely precise quantum compass that would eliminate the bias and scale factor drifts commonly associated with gyroscopic components. Then it can be used in seismology. Then we'll say towards the last part. So what are the limitations of the quantum computing or quantum? Firstly, quantum computers at present are too large and they require near absolute zero temperature for effective function. That is the limitation. Key size is too large. Second is temperature. Absolute zero temperature for effective function is required. This may hinder the portability and commercial adoption of these computers. This is the limitation. Secondly, qubits are extremely susceptible to noise. We can say if somebody handles some thing is happen, then noise is generated, so completely output is completely affected. So qubits are extremely susceptible to noise. Any disturbance in temperature, electrical energy and sound energy will destroy the qubit's superposition state. Lastly, these qubits are present for a very short period of time, which means the computation should be carried out as quickly as possible after the formation of qubits. Once the qubits are formed, we have to compute the way. So qubits are present for a very short period of time. Otherwise, due to decoherence, the qubits will get destroyed and change into classical bits. Just like qubits, that means when we throw a coin in the air, it takes some time, certain amount of time to come it at the ground. So before it falls at the ground, we have to take different positions of that coin. Once it dropped at the ground, we can say either head or tail. In the same way, a qubits present very short period of time, which means the computation should be carried out as quickly as possible after the formation of the qubits. Otherwise, due to decoherence, the qubits will be destroyed and changed into classical bits, just like either head or tail. So apart from the above mentioned challenges, the development of quantum algorithms for effective resolution of various computation problems serve to be a significant challenge. That means for different applications, you have to need some completely different types of algorithms. So that is also the challenge. Now, what is the post-quantum world? There is a good chance that quantum computer will able to crack RSA 2048 within 5 to 10 years. Need about 8,000 qubits in a universal computer to do this. But what happened? IBM already announces in 2023 1,000 qubits in a universal. So for 8,000 qubits, it takes lots of time. Some encrypted data has a shelf life of more than 10 years. It may take 10 years to cut over to a new encryption scheme. So companies and governments are scrambling to figure out what to do. That means if suppose RSA is cracked, now most of the organizations, they use RSA as a secure algorithm. Now what happened after 5 to 10 years? Most encryption used today is not safe in quantum world. If someone has been recording a HTTPS session say they may not be able to decrypt it now, but a few years from now, who knows? There are encryption algorithms that are safe. Secure communication will move to symmetric encryption or hash algorithms, and perhaps lattice algorithms may be new technique. Then quantum key distribution, QKD, will likely be more popular for the most sensitive communication. Some governments and banks are already starting to use quantum safe algorithms, and this is expected to increase over the next decade. It may take 5 to 10 years to replace infrastructure and software. This is the major problem again. It is the right time, I think, to start moving to a post-quantum secure world now. Otherwise, it will create a problem. India depends for chips. You know, automobile industry, everything is automation is there. So there is a shortage of chips in the last 2-3 months, and now our government is going for developing the chips ourselves. So, but again, to develop the infrastructure, it takes 2-3 years, and then only the production will start. So for this, it may take 5 to 10 years to replace the infrastructure and software in quantum computing. It is right. It is the right time, I think, to start moving to a post-quantum secure world now. Now, I want to conclude my session. From quantum computing is currently in its nascent state. It does not appear to have significant benefits in many computational problems compared to classical computer. Several experiments performed on a small scale quantum computer is that the performance of this computer may be better and faster than conventional computers. So numerous applications are being provided by the researchers in various domains. So all these things are there. So one can only imagine the revolution a matter portable, efficient, optimized quantum computer can bring, which would then open up new industries entirely and move the world into the next era of computation. So currently, we just wait and watch and try to develop the situation so that we can use this quantum computing easily after 5 to 10 years. That's all. Thank you all for listening me. Any queries you can ask. These are the references. Any questions? Welcome.
Thank you, sir.
Welcome, madam.
Yes, any query from participant side? Please ask your query, unmute your mic, also turn on your video if you are having query. Yes, participants, those who want to ask query, please turn on your mic and turn on video also. Yes, participants.
Okay, thank you. I think they're already aware about all these things. Thank you, because these are the very emerging areas, and no
Yes, sir.
that much technical things are not there. And I think this is my contact mail ID. You can always welcome on this mail ID for any type of queries. Then thank you to the organizing team, basically, More sir,
Haan, sir.
Yawalkar sir, and
Okay, sir.
Bharat sir, head, for giving me the opportunity to,
Yawalkar sir bola.
because I am already new in this domain also. I have actually, when I received the call from More sir, I have trying to, okay, we can take the challenge so that I also learn something about quantum computing. And that's the benefit for me. Today I get at least something about quantum computing. And
Excuse me, sir.
yes. Yes,
Just,
madam.
I am having one query.
Yes.
Since
Madam, can you turn on your video?
for
Hello.
Madam,
Madam, can you turn on your video? Madam.
1 minute, sir. Oh, hello. Am I audible?
Yes, sir. Yes, yes.
Yes, you are audible, ma'am.
Yes, madam. Go ahead. some network issue.
Hello, Maitre madam.
Hello, Maitre ma'am. Are you there?
Okay, my mail ID is already given. If she have any queries, she can contact me. Definitely. Some network issue may be there.
Maybe some network issue will be there.
Thank you, Pachghare sir,
Thank you, sir.
for sharing your valuable expertise in this area. No doubt it is an emerging area, but still giving your thought in detail, giving all the details.
On behalf of Computer Engineering Department, I would like to express our gratitude towards you for the valuable knowledge and time you shared with all of us, sir. The things which you focus regarding the future of quantum computing and opportunities surely encourage the researchers for the new research in quantum computing. As this is one of the emerging technology in this field, we came to know many technical things, its limitations, the basic differences between quantum computing and classical computing, as well as the post-quantum world, which help all the participants for the better understanding of minute things in quantum computing. So at the end, also I am very much thankful to you, sir. Thanks a lot.
Thank you, madam.
Thank you very much, sir,
Thank
for
you,
your
sir.
valuable time for our FDP.
Can I leave, sir?
Yes, sir. The session is over, and
Okay.
today all three sessions are over.
Yeah.
So participants are requested to submit your attendance and feedback also. Attendance link and feedback.